Hi folks, in this video we're going to talk about polynomial approximations of functions, which I might call an introduction to the Taylor recipe. So here's the motivation. A tangent line at an argument can be thought of as a linear approximation to the function at that argument. I mean, if you look carefully at the point of tangency, you see that the tangent line and the graph of the original function sort of coincide for a while, or they come very close to coinciding. So you can think of this as sort of a linear approximation. So now a quadratic polynomial allows for some bend as opposed to a linear function. So a quadratic might be better able to approximate the function over a larger interval. So if you allow some bend, maybe you can get this thing to look really good for more arguments than the linear approximation was able to do. So we could call this a degree 2 approximation, and the linear approximation was degree 1. And then obviously you could ask yourself, can I kick the degree up? Is there a sort of degree 3? So a cubic can bend a bit more than a quadratic. Can we create an even better approximation if we use a cubic polynomial? So, you can imagine that, yeah, it fits better over a wider interval. And how about polynomials of degree n? What happens if you just let the degree get higher? So that's the motivation. And what we're going to do is, instead of sort of develop a theory and then look at examples, we're going to look at examples and then summarize the theory. So let's just plunge right in. So there's the function 2ln of x plus 3. And so let's find the linear function L that best approximates this function at the argument x equals 0. So this is really no different than the kind of problem you first saw when you started studying differential calculus. We could just rephrase this as find the tangent line at x equals 0. So what does the solution look like? We know that f of 0 is 2 ln of 3. So we know the point 0, 2 ln of 3 is on this graph. And we take the derivative and we get 2 over x plus 3. And if we evaluate this derivative at 0, we get 2/3. And that tells us that this tangent slope at this argument is 2/3. Now we're just going to put the pieces together. So our linear function has to be 2/3 x plus 2 ln of 3. And we could go back to Desmos and plot this relative to the original function. And there you have it. This is our tangent line. And we can think of this as being a linear approximation to the function. All right, well, let's play the next most complicated game. How about find the quadratic function q that best approximates this function at the argument x equals 0. So we already know that f of 0 is 2 ln of 3 and f prime of 0 is 2/3. So let's just hold on to those facts because those are going to be useful in a moment. So we seek a function of the form ax squared plus bx plus c. And if we want q and f to behave similarly near x equals 0, then we might expect that, well, certainly we want the function values to be the same. And we would certainly expect the tangent slopes to be the same. I mean, we know that this function should be sort of shooting along the same tangent slope if it's going to be a good approximation. And now the question is, what other information can we use? So a good conjecture here is just going with the pattern. Maybe we want the second derivative of q evaluated at 0 to match up with the second derivative of f evaluated at 0. Now, this is just following the pattern, but the speculation, if we try to imagine what the theory is, perhaps the value of the second derivative at an argument determines the bendiness near the argument in some sort of abstract way. And if we could equate these two things, maybe we can control just how much bendiness there is at that argument. So let's play this game. Let's shoot for that. So we know that the first derivative of this quadratic has to look like this, and the second derivative has to be the constant 2a. And when we plug in 0, we get c, b, and 2a respectively for the values of the original function, the first derivative, and the second derivative when we plug in 0. So we think that these quantities somehow control the behavior of q near x equals 0. And so we want to sort of match these up with the corresponding values for f. So f of 0 is 2 ln of 3. F prime of 0 is 2/3. We already knew this. Now we're missing this last spot. So let's go back and calculate the derivative, the second derivative of f. We already know the first derivative was 2 over x plus 3. And I'm going to write that as 2 times x plus 3 to the negative 1. So I can use the power rule to take the next derivative. So that should be just negative 2 x plus 3 to the negative 2. Otherwise known as negative 2 over x plus 3 quantity squared. And when I plug in 0, I'm going to get negative 2/9. So that's what's missing here. The second derivative of f at 0 is negative 2/9. So now we need c to be 2 ln of 3. We need b to be 2/3. And we need 2a to be negative 2/9, which means, doing a little bit of arithmetic here, a has to be negative 1/9. So now we're going to take these coefficients and we're going to plug them back into our quadratic. And this is apparently the formula for the quadratic we're looking for. It should be negative 1/9 x squared plus 2/3 x plus 2 ln of 3. And once again, we're going to appeal to Desmos, and we're just going to plot this and look at it. And sure enough, this is looking awfully good near x equals 0. It's bending right along with the curve over an interval from, say, negative 1 to 1 roughly. You can really see that it's doing a good job graphically, at least. And by the way, notice that the linear approximation is already sitting here inside of the quadratic approximation. So the higher degree approximations are going to carry with them the lower degree approximations. So if we kick this up to the next level, if we look for a cubic function, why don't we just use what we already have for the quadratic part? So if we're going to find this cubic, then we already know the quadratic approximation at 0. So now let's look for a cubic function, and we're just going to assume that this piece is already in place. We already know that q of x is equal to that. So the second degree, first degree, and constant terms are going to be what we already know they are. So now what? We need to fill in the last piece of this puzzle. We need to figure out the third derivative of c and compare it to the third derivative of f, both evaluated at 0. And again, we wonder why this is going to work. Perhaps the value of the third derivative at an argument determines sort of higher order bendiness or bendiness of bendiness. We don't have good names for these things, but somehow these higher derivatives are perhaps controlling sort of various degrees of wiggliness in the graph. So let's just match up these coefficients and see if it works. Here's our derivative of c, here's our second derivative of c, and then the third derivative of c is just the constant function 6a. And when we plug 0 into that, of course, we're going to get 6a. Now, here is our second derivative of f. We need to calculate the next derivative, the third derivative, and using the power rule, that's going to be 4x plus 3 to the negative 3, otherwise known as 4 over x plus 3 cubed. When we substitute 0 into that, we get 4/27. So that's the missing piece here. We need 6a to match up with 4 over 27, which means when all the dust settles, a has to be 2 over 81. That's our missing coefficient. So we're going to plug that in back into the formula for c. And again, we're going to just plot this on Desmos, and boy, this is really looking good. And this is looking good over an interval that stretches, a little bit beyond 1.5, and to the left of negative 1.5. It's looking very, very good. Okay. Now let's switch gears. So what we're going to do next is we're going to find another cubic approximation. We're going to switch up our function, and we're going to find this approximation at an argument other than 0. So our function is going to be sine x plus a half. And we're going to try to approximate this function with a cubic polynomial at the argument 5 pi over 6. Now things are going to get more complicated, and we're going to figure out how to cope with that complication, and that's going to help us see what the template is for the general problem. So we're trying to make all of this happen near 5 pi over 6, so just keep that in mind. So here's the function, the first derivative, the second derivative, and the third derivative. And we're thinking that the values of these functions control generalized bendiness, whatever that means, at various arguments. And we care about the argument 5 pi over 6, so we're going to be plugging in 5 pi over 6 to all these functions. And you should double check all this and review, polish off your trig if you need to, but these are the values of f and the first derivative and the second derivative and the third derivative, all at 5 pi over 6. So now here's our approximating cubic function. And the first thing we're going to do, we're going to change up the way we describe the coefficients. So let's be systematic about this and use constant names with subscripts. And so we don't run out of letters, right? Because if we just use A, B, C, D, E, F, G, that's not going to provide any kind of regularity. And by looking at the subscript, we can match up what constant belongs to which power. So a3 should belong to the cubic term, and so on. So we'll be a little more systematic about that. Now remember, we're doing this at 5 pi over 6, so one of the things we're going to be doing is we're going to be plugging in 5 pi over 6. Now look at this polynomial when you plug in 5 pi over 6. That is just going to be a mess. We don't want to have to deal with this. So we're going to make one other adjustment. We're going to expand the polynomial in powers of x minus 5 pi over 6. So what do I mean by that? This is what our polynomial is going to look like. Okay, now take a look at this. It's a perfectly reasonable polynomial. If you were to expand all these out and collect the terms, you just get a cubic polynomial. But the reason we're doing this, you might think this is making it more complicated. Actually, it's making it less complicated because when you plug in 5 pi over 6 to this expression, very nice things happen, as we'll see in a moment. So here's our cubic polynomial, and we need to find these coefficients a0, a1, a2, and a3. Now, taking the derivative of this polynomial is no problem at all. The power rule kicks in, the chain rule spits out factors of 1 from each of these terms, so there's really nothing going on with the chain rule. So we can find derivatives easily. And so here they are, and you should double check these. And now watch what happens when you plug in 5 pi over 6 for x. Most of these terms vanish because you're just going to get zeros floating around. So there are the results of plugging in 5 pi over 6. It's a snap, so that's nice. We don't have any ugliness when we try to simplify the values of these things when we plug in 5 pi over 6. That's really why we express this polynomial in powers of x minus 5 pi over 6. Okay, now remember what we're trying to do. We're trying to match up the function values and the values, the corresponding values of the approximating polynomial at the argument 5 pi over 6. So we should choose a sub 0 to be 1. We should choose a sub 1 to be negative root 3 over 2. And we should choose a sub 2 to be 1/2 of negative 1/2, otherwise known as negative 1/4. And then a3 should be 1/6 of root 3 over 2, so that should be root 3 over 12. So these are our coefficients. This was our template for the original cubic polynomial that we hoped approximated the function well. So we're going to plug these in, and when we do that, we get this result. So here is what we believe to be the cubic polynomial that's going to do a good job of approximating this function near the argument 5 pi over 6. And notice, by the way, this is something we mentioned a few slides ago, we get the quadratic and linear approximations for free from this process. They're built in. Here's the quadratic approximation, and here's the linear approximation. You just knock off the higher degree terms, and those are going to give you the lower degree approximations. So now, here's a Desmos plot of the linear approximation, i.e. the tangent line. Looks familiar. Here is a plot of the quadratic approximation. Looks a little better than the linear approximation. Here is a plot of the cubic approximation. You can see it's even better. So it appears to be the case that the higher the degree of your polynomial approximating the function, the better you can get it to bend and wrap around the original function. So let's just try to graphically represent where the approximating function and the original function f sort of agree to the visible eye. So here's where the linear approximation looks good. Here's where the quadratic approximation looks good. And here's where the cubic approximation looks good. So you can see that the ability to approximate the function is getting better as we increase the degree of the polynomial that we're using to approximate the function. All right, so if we want a general theory, we need to look at some properties that are going to help us piece this together. So let's look at an example of a phenomenon that comes into play. So if you take the derivative of x to the 5th, you get 5x to the 4th. If you want the second derivative of x to the 5th, well, that's clearly going to be the derivative of the first derivative, and that's going to be 4 times 5 times x cubed. And then if you want the third derivative of x to the 5th, you should take the derivative of the second derivative, and that's going to be 3 times 4 times 5 times x squared. And you keep playing this game until you get down to the 5th derivative of x to the 5th. And you get, that should look familiar to you, that is nothing more or less than 5 factorial. And you should work through a couple examples and convince yourself that quite generally it's true that if you take the nth derivative of the power function x to the n, you're going to get n factorial. This comes up all the time in what we're doing. And by the way, it's pretty clear that if you took the next derivative, the n plus 1th derivative, you'd get 0. So you can only take the derivative of x to the n times, and then it's going to vanish. So that's something to remember. Let's talk about this trick of centering a polynomial at an argument. So this polynomial here, we'll call it a polynomial degree n that's centered at the argument c. And what we mean by that is we're going to use, instead of powers of x, we're going to use powers of x minus c. Now, when we take derivatives of such a thing, there's no problem. All right. So you should pause and double check these calculations, but the derivatives go pretty much as easily as standard derivatives that are expanded in powers of x to the k. And one of the things to notice is this relationship here between the coefficients that show up in your original polynomial and the constant terms of the derivatives. There's this relationship, and it persists throughout all these derivatives. So let's pin this down. We're going to substitute c for x in each of these. Now watch what happens. You plug in c for this, most of these terms vanish. You just get a naught. Plug in c to the derivative, it almost all vanishes. You get a1. Plug in c to the second derivative, you get 2 factorial a2, and so on. So we're going to go right on down the line, and we're going to plug in c to this polynomial, and you get these beautiful constants. So it follows that whenever you have a polynomial centered at c, the values of the higher derivatives of that polynomial evaluated at c are given to you by this nice, beautiful formula. So the kth derivative of p evaluated at c is just k factorial times the coefficient a sub k. And this works for k equals 0, 1, 2, all the way up to n. And you might wonder about the case of k equals 0. That looks kind of strange, perhaps, but recall that 0 factorial is defined to be 1. That's a definition, a standard definition. And if we just interpret the 0th derivative of p to be just the function p itself, you don't do anything to it, then this formula becomes p of c equals a naught, which agrees with our formula for p. So it's all good. And this is the formula we're going to use moving forward. And the motto here is when you center a polynomial at an argument, it is easy to work with the values of the higher derivatives at that argument. Okay, it's time to turn to what I call the Taylor recipe. So the mathematician Brooke Taylor did his work at the end of the 17th century and into the 18th century. And he was the first to publish the theory surrounding what we're about to do. So here's what I call the Taylor recipe. Given a function f and argument c, find the coefficients a0, a1, all the way up through an, so that the polynomial you get when you construct this polynomial here, centered at c, provides the best approximation of f possible near the argument c. Now I have best in quotation marks because we have no way of sort of quantitatively describing the situation here, what constitutes best. And that's part of the theory moving forward of Taylor series and Taylor polynomials. But just based on the examples that we've seen, we sort of intuitively know what that might mean. So we've got a function f, and we want to find a polynomial of degree n. And so what's the connection between them? Well, first of all, we better center our polynomial at the argument c, since that's where all the action is taking place. We want Pn to approximate f well near c, so we'll center our polynomial near c. We anticipate having to find the higher derivatives of f all the way up to the nth derivative, and we need the values of these derivatives at the argument c. And one of the things you should notice right away is this function had better be differentiable n times at the argument c, because if you can't take n derivatives and evaluate those derivatives at the argument c, you can't even run this recipe. So that's going to be one of the prerequisites for you to even be able to apply this recipe, is the function had better be differentiable at least as many times as the degree to which you're trying to approximate it. So we anticipate that this collection of numbers somehow is controlling the behavior of f near c, And we want to match that up with the behavior of a polynomial Pn near C. So we want these values of the higher derivatives of Pn to match up with these functions. And we now have this principle that says, you know what, if you want the values of the higher derivatives of the polynomial, you just use this slick formula. So that's going to translate into this information right here. So let's put this off to the side, and we realize that we want these to match up, and that means we should choose A naught to be f of c. And we want these two numbers to match up, so we better choose A1 to be f prime of c. And we want these numbers to match up. A2 had better be 1 over 2 factorial times the second derivative of f evaluated at c. A3 had better be 1 over 3 factorial times the third derivative of f evaluated at c, all the way down the line until a sub n should be 1 over n factorial times the nth derivative of f evaluated at c. So here's our recipe. You can see the pattern. It's quite evident in this list. The recipe for finding the coefficients ak is to choose ak equals 1 over k factorial, kth derivative of f evaluated at c. And we're going to call this the Taylor recipe. And by the way, the polynomial we get, we're going to call that resulting polynomial the nth degree Taylor polynomial for f centered at the argument c. So let's give this Taylor recipe a test drive on one last example. So we're going to find the 5th degree Taylor polynomial for the function ln of x centered at the argument c equals 1. So we know we need the derivatives all the way up to the 5th derivative of ln of x. And if we use the power rule, we can calculate these pretty efficiently. So we're going to get these formulas for these derivatives. We need to plug in 1 into all these derivatives because that's where the action's happening. And we get these numbers right here. Now we're going to use the Taylor recipe, so we know to take those numbers and divide by the appropriate factorial value, and we get a collection of numbers that looks pretty nice. It's 0, 1, negative a half, 1/3, negative a quarter, and 1/5. And we're going to assemble that all into our 5th degree polynomial like so. Now, here's the plot on Desmos, and you'll see that I used sigma notation to help put this in a little more efficiently, and you should work out the sigma notation to make sure that you are indeed getting the same polynomial as I've got written on the bottom. But here's a comparison of the graph of the logarithm function and this 5th degree polynomial near x equals 1, or c equals 1. And we'll notice that on this interval here, the visual distinction there is no visual distinction there on this interval, and it starts peeling away beyond that. But this does a pretty good job over this interval. So we're going to end this video with a few good questions you probably have. Does the Taylor recipe always create a polynomial that does a good job of approximating the function? And if it does, just how well and on how large an interval can a Taylor polynomial approximate a function? And then, most intriguing perhaps, what happens if we simply keep applying the Taylor recipe? In other words, you don't stop at degree n, you just keep cranking out those coefficients and you assemble them into a power series. What does that power series do for you? So all of this is wrapped up in the theory of Taylor polynomials and Taylor series, and that'll be the subject of the next few videos.